Hey guys, this is the oral tryout part 1 solutions. I think I'm going to make two different videos, one for algebra and one for the other stuff. So yeah, just so the video's not too long. So, okay, first one's pretty simple. I didn't ask anybody yet because I thought it was pretty, it was just like a good intro one. Basically, to prove this, you can choose any integers m and n, right? Such that they're both integers, right? So if they're integers, that means that 2m plus 1 and 2n plus 1 are guaranteed to be odd. If m and n are odd, or if m and n are even, 2m plus 1 and 2n plus 1 will also be even. So we just need to prove that if we square them both and add them, let me make that a bit more clear. If we do that, then this result is even. So we can later distribute this out. 4m squared plus 4m plus 1 plus 4n squared plus 4n plus 1. That's equal to 4m squared plus 4n squared plus 4m plus 4n plus 2. You can factor out a 2, and then it doesn't even matter what this is. That 2 guarantees that it's even, so we finish the proof. So yeah. Next one, basically, wait, let me read it again. Okay, so the product of all the terms, that's just going to be a times ar squared, right, times ar to the n, right? So using exponent rules, that's just ar to the 1 plus 2 plus 3 plus all the way up to n. So that's just equal to ar to the n times n plus 1 over 2, which is just, yeah, which is does that, right? And that means that k, for r to k, to divide it, r to the k must be less than or equal to r to the n times n plus 1 over 2. That means that k must be less than or equal to n times n plus 1 over 2, meaning that the largest integer k must be n times n plus 1. Now, there was one thing. You had to show that, or you didn't have to, but you had to at least consider the fact that, hey, k is an integer, and you need to explicitly say that this is guaranteed to be an integer because n and n plus 1, one of them is guaranteed to be even. But yeah, I didn't really care if you didn't mention that. It would just be nice to. So that's your final answer. Okay. So yeah. And notice that it's guaranteed. If A contains some one of R, it could be greater, but yeah, it's just guaranteed. So yeah, okay, exercise 3. Let me see. Basically, okay. So this one is pretty simple. If you consider it like this, S of n is the perfect square. S of n plus, or S of n, that's actually just equal to the S of n minus 1 plus something, right? That's just that's what the recursive formula anyways is. So what that something is, you could just show it by hand. For example, one sec. Okay, sorry. So yeah, so S of n minus 1, you have to show what's it adding to, right? So if we look at the first one, where n, and then you have S of n, if n is 1, S of n is 1, right? If n is 2, then the nth perfect square, so the second perfect square is 4. 4 minus 3, that's equal to, 4 minus 1 is equal to 3, right? N, when that's 3, S of n is 9, then it's 5, right? And you'll notice a pattern. You'll notice that it's every odd integer added. So you just take the odd integer, you take the second odd integer, or in respect to it. So it'll just be 2n minus 1, right? For example, if n was 2, it would be 4 minus 1 is 3. So you just add the odd integer that is 1 less than 2 times the n. So that's the formula. And you don't need to, well, I mean, I'm not going to show that it works because I know this is the formula for sure. But one thing that you could use to show is that since s of n is the nth perfect square, you could just say s of n is equal to n squared. So you don't even have to like show that. You just can do n squared plus 2n minus 1. I know this is not a recursive formula, but for this example, you could use this. So yeah. So now b is pretty like cool because like a lot of you could just draw out the dots and then have that, but I wanted you to actually show what it meant with respect to area. So if I have 16 dots here, right, this is equal to s of 4. Now this over here, or this square over here, this is n minus 1 and this is n minus 1. Therefore, all of these are just n minus 1 squared, which also happens to be s of n, right? Now this, the extra stuff you're adding, if you notice, this is an n, and this is an n minus 1. Therefore, the entire thing just becomes s of n plus n minus 1. Well, that's just s of n plus 2n minus 1, which is this. So yeah, that's pretty much this problem. Yeah, I was really looking for the area, not like just saying it worked, but like actually like showing the respect with area. Okay. So this one, basically, the a of n, that's just an arithmetic series. That's just start. The general form is a plus d times n minus 1. You didn't have to write that, but just for the solution. So a of n, that's just equal to 5 plus the common difference is 6 times n minus 1. That would be enough. You didn't have to like expand it. You could like just simplify it to 6n minus 1. Now what's the next part? So a new term, or a new expression, b of n, that's just equal to that's just equal to a of n squared plus 5. So to show that it's divisible by 6, you literally just substitute a of n into b of n, because b of n, that's just equal to 6n minus 1 squared plus 5. Let's go to 36n minus 12n plus 1 plus 5. 36n, oh, forgot the square here. 36n squared minus 12n plus 6. That's equal to your thing, right? You need to prove that's divisible by 6. Well, boom, you can just factor out a 6 from that. So that's just 6n squared minus 2n plus 1. This is guaranteed to be an integer. That's just an integer, and this is just 6, so it's always going to be a multiple of 6, or it's divisible by 6. And then prime factors that it must be divisible by, you have no clue what this is, so you're only looking at prime factors of 6, which are just 2 and 3. So yeah, so that's pretty much all it is. You don't really know for sure what it could be. There might be a way, I'm not sure if there is. I'm like 99% sure there isn't a way to find out what it's guaranteed to be, because you could always find a counterexample, but yeah. Okay. Because, you could just say that, oh yeah, I remember now. 6n squared minus 2n plus 1, you have to show that this isn't factorable. And it's sort of easy to show that because b squared minus 4ac is not an integer, right? 4 minus, well, that's just not even real. This one has no solutions, right? This is 24, less than 0, so not factorable. So yeah. Okay, exercise 5. Okay, so deriving the sum of a finite geometric series. Well, remember, the sum, let that just be a variable s. There's a plus ar plus ar squared plus dot 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 plus ar to the n minus 1. There's not really much, like, you literally just have to memorize this or like know it in advance, which I expected you to do because you have 2 weeks to do this prior. S, take S, right? You want to cancel out, you want to make it such that it's like telescoping, which means a lot of stuff cancels out. That's like a trick to find a formula. So a really, really easy way to do that is just, hey, I can cancel out a lot of the middle terms by just doing s times r is equal to ar plus ar squared plus ar cubed plus up to ar to the n, right? Because you're multiplying by that extra n. SR minus S is just equal to these two, everything cancels. So, and then all these dots cancel. So you're just left, and this cancels too. So this is AR to the N minus A. Factor out the S because we're solving for S. So now you just have A to the R to the N, A times R to the N minus 1 over R minus 1 is equal to the sum. So yeah, that's pretty much it. Then for B, the infinite series, well, instead of having this close off at AR to the N, this just goes on to infinity. So I'm not going to write the entire thing, but SR minus S would just be everything would cancel on one side, and then it would be 0. The other one would just be minus A. And that means that S times R minus 1 is equal to negative A. So S is equal to negative A over R minus 1, which means S is equal to A over 1 minus R. And that's the finish. But you do also have to say, like, this was like another thing. Sorry, just got a text. Okay, and you do have to say that the absolute value of R is less than 1. That's like an extra thing. I know I would have forgotten it, so don't beat yourself up if you forgot to say it. But yeah, just make sure you say it just as like a precondition. But yeah, okay. This one had a typo, so I didn't ask anyone it. 1 second, I'm just gonna reply to this because it's pretty important. Okay. So for this one, you just have to prove Vieta's formula. So basically, best way of doing it, let P of X be in its factored form, which means that it's just factor out that A naught. It'd be X minus R1, X minus R2, right? Up to X minus R to the N, or R sub N, right? That's P of X. So, basically, if you want to show what it is, you have to realize that, hey, if you take if you expand this entire binomial, or not binomial, sorry, polynomial, and return it into a polynomial, so it's like right now in factored form, you have to expand it. This last term, you would have no x's in the last term, and the constant term would literally just be x A naught times negative R1 times negative R2, right, up to negative Rn, right? I'm including the negatives because this is technically like x plus negative R2. Now, what is that even equal to? Well, that's equal to this last constant term, A sub n. So that's equal to A sub n. And now An over A naught is our generalized form for negative R1 times negative R2 times all the way up to a negative Rn, right? And this is where like you kind of have to like I wanted people to take this and apply it to both problems to save time, and nobody really had the opportunity to because I never asked it. But to consider this, right? If n is odd, then we have an odd number of negative 1s. Therefore, you can rewrite that as negative 1 to the n, and if n odd, then that's just equal to negative 1, right? If n is even, then negative 1 to the n is equal to 1. So what does this mean? Well, here, if n odd, then this just equals to A sub n over A sub naught over negative 1 times the product, which I'll just say as P, right? And then, yeah, that works out because then P is equal to negative n over A naught, right? That's just the finish, right? But if n is even, sorry. if n is even, then a sub n over a sub naught is just equal to p, and that's just it. So those are your two formulas that you needed to show. So yeah. Okay, last one, pretty cool thing. It was induction, which, like, it was nice that I asked this question a lot, and it was very cool that a lot of people knew what they were doing. Oh crap, what did I do? Oops. Okay, cool. So basically, first off, for induction, you just need to show base case, right? Oh, sorry, I can't spell. Base case. So that means that for it, let's just say that if n is greater than 0, well, I kind of forgot to write this, but like you're assuming that n is an integer, therefore n is equal to 1, right? Because technically if n is greater than 0, then we're looking for n is greater than or equal to 1. That's the assumption we're making. So if n is 1, then the formula would just be 1 squared plus nothing else is equal to 1 times 2 times 3 over 6. Well, yes, that works. So base case is proved. Now the inductive step, that's just equal to, like, what if we do, assume that it works for k, right? And we try in k plus 1, right? Sorry, I hit the mic. But then that just means that we're trying out for 1 squared plus 2 squared plus so on, right? Plus n squared. We're adding that k plus 1, which is just equal to n plus 1 squared. And that should equal to, well, whatever we had, n plus, or, well, the formula, if we plug in n plus 1, which is n plus 1 times n plus 2 times 2n plus 3, and that's over 6, right? Again, you can just write this using summation notation as well, where it's just equal to this, and then you're adding that extra n plus 1 squared. That should be equal to this. And if it does, well, this entire thing should ideally just be the formula which we assume works, which is n times n plus 1 times 2n plus 1 over 6 plus that n plus 1 squared is equal to n plus 1 squared times, oh no, sorry, times 2, no, n plus 2 times 2n plus 3. And that's all over 6. So now we have to prove that these two are equal. You're only supposed to really manipulate one side of the equation. Like, it's not really good to, like, cancel stuff out. But I guess you can. Like, if you, like, assume that they're both equal, you can, like, continue to manipulate both sides until you run into a contradiction. But for this case, I'll just show how it looks if you only manipulate one side. This would just be equal to n plus 1 factored out times n times 2n plus 1 over 6 plus n plus 1, right? That's all on one side. And I'm just going to say RHS for the right-hand side. Then you can throw a 6 in front of here. So that's 2n squared plus n plus 6n plus 6 all over 6 times n plus 1 is equal to RHS, right? Then it's n squared, or 2n squared plus 7n plus 6 over 6 times n plus 1 is equal to right-hand side. Then this is pretty easy to factor. You're looking for two numbers that multiply to 12 and add to 7. That is just 2n squared plus 6n plus n plus 6. Right? Wait. No, that is not. That is n plus 3. Right? Wait. Why can't I factor? No, two numbers add up to 12, right? So 6 and 1 work. Yeah. Okay. Cool. Oh, sorry. Wait. Oh, because this doesn't even work. This is wrong numbers added. That's why it wasn't making sense. 4n plus 3n over 6 times n plus 1. And then I'm just going to factor that as 2n times n plus 2 plus 3 times n plus 2 over 6. So if you notice, that just turns into n plus 1 times n plus 2 times 2n plus 3, right? And you don't have to show for an actual orals competition, you don't have to show the entire setup, because that takes a lot of time. You just have to like show that, hey, like the algebra works out, this works. So yeah, but yeah, it's just equal to, oh crap. Yeah, if you just notice, it's the same formula. But yeah, I'll just paste this down here and then boom. Yeah, that works out. So yeah, it works. The formula is proven by induction. So yeah. And yeah, those are all the problems. So I'll make a different video for the number theory and probability stuff. So yeah.